Professor Peck received his degrees from our RPI, and he worked as a structural engineer before he turned to the dark side. He went to Harvard, worked with Arthur Casagrande, and there he developed a connection with Carl Terzaghi, and he was selected as Carl Terzaghi's representative on the Chicago subway. You can see now we have some connection to our Terzaghi, to our Peck lecturer today. And then with that transition, Professor Peck joined the University of Illinois and helped establish a world-class program in geotechnical engineering. Of course, I'm very objective about that. And the University of Illinois is where our Peck lecturer started his academic career. Professor Finno received his bachelor's degree in civil engineering at the University of Illinois. But he decided to explore the West Coast for a few years, where he got his master's at the Stanford University, you know, that university a little bit south of San Francisco. And then he worked for a little bit at Sargent Lundy and Woodrow Clyde, which I discovered that's where he met our current, this year's seed lecturer, Professor Kramer. And also, I found also through that connection, Professor Kramer also had a connection with our Terzaghi lecturer, Rudy Punapart. It's all the Chicago connection, okay? So, and I'll leave it there. So, afterwards, Professor Finno kind of came to his senses and decided to pursue a PhD in geotechnical engineering, and then moved back to Illinois, where he is a professor at Northwestern University. And he also got to work on the Chicago subway as well. If you've read some of Professor Finno's papers, he had a number of papers related to some of the excavations. So he has conducted research in the areas of full-scale performance of deep excavations and tunnels, adaptive management methods in geotechnical engineering, numerical analysis, inverse analysis techniques, failure processes in soil, small strain behavior of clays, and non-destructive testing of deep foundations. He also received a number of awards from ASCE, including the Carl Terzaghi Award, the Harry Schnabel Award for Lifetime Achievement in Retaining Structures, the Walter L. Hubert Civil Engineering Research Prize, and the Thomas Middlebrooks Award twice. He is the author and co-author of more than 175 reviewed technical papers. He served as chair of the Earth Retaining Structures Committee and as editor of the Journal of Geotechnical and Geoenvironmental Engineering. And he has consulted on and continues to consult on more than 300 projects for many organizations on projects related to retention systems, tunnels, shafts, and slopes. Now, on a personal note, I have known Professor Finno for a while as a student. As I got to learn about deep excavations, I read his papers. Then after I moved to Illinois, we collaborated extensively in research on at least 2 research projects. We've written papers together, and so it has been really personally a pleasure to get to know, and an honor to get to know Professor Finno both as a mentor and as a colleague. So please join me in welcoming Professor Finno, our 2018 Peck Lecturer. And as a Peck Lecturer, Professor Finno receives the Peck Medal. So,
Well, thank you very much, Yusuf. It was an overly effusive introduction, but I appreciate it nonetheless. It is a great privilege to be able to give this lecture in the memory of Professor Peck. But before I get started, though, I do want to acknowledge that certainly anything that I've accomplished over the years has been done with a lot of help. And so before I get started and forget about everything, I want to talk about the people that have helped on most of these projects that you're going to hear today. I've had the good fortune to work with supportive excavation subcontractors, specialty contractors that provided in-kind support and their expertise. I was able to work with some very good general contractors that allowed myself and students to run around their excavation sites. I worked with some very good engineering firms that have provided their expertise. The funds have been provided by, over the years for these particular projects, have been provided by the National Science Foundation and the Infrastructure Technology Institute. And of course, as every academic in this room knows, that we would not accomplish anything without the support of our students and the contributions of our students. And so, since I've been limited to 50 minutes, I can't read all these names, but without their help, this not would have been possible. So, Professor Hashash gave us a nice introduction about Professor Peck, and everybody knows he was a fantastic, well, maybe not know he's a fantastic teacher. I had the personal pleasure for that honor, but he was also a wonderful engineer and a great researcher. In fact, when I was an undergraduate in the 1970s at the University of Illinois, he taught a course, or I had to take a course called Introduction to Foundation Engineering. And not knowing what went on, I just signed up for it at a convenient time, and the instructor popped up with the name of R.B. Peck. And I had no idea that I was in for a treat, because after 2 weeks or so, it became very clear that he was a wonderful lecturer, and he always was extremely clear. And in fact, when he was the first professor I ever had to show slides, this is in the 1970s, slides of construction, and then he was able to relate that construction to whatever we were learning in class. So it was just a wonderful experience. If we fast forward then to about year 2007, I believe, was Geo Denver, when Professor Peck and Professor Osterberg were being nominated or being honored by Geo-Institute as legends of the Geo-Institute. There was a ceremony for them. And after the ceremony, we were milling about, and I decided that I'd go tell Professor Peck that, if it wasn't for you, probably not have, you were really very influential in getting me as a geotechnical engineer, and I never would have gone into this field. And so he looked at me, and he just, which I swear to my grave was a twinkle in his eye, and he said, well, you know, Rich, you can't win them all. So the other thing about Professor Peck is that you may not know, he had the title, this is a real title, that he was the assistant subway engineer for the city of Chicago in 1939 to 1942. And so this is where he collected quite a bit of data in terms of that provided the basis for the earth retention system design for stability, looking at apparent earth pressure diagrams. So with that, I want to really talk about a little bit about the basis of design, and that's the stability-based design pre-1980, which Professor Peck had vast influence on, and serviceability-based design, where we're looking at designing for limiting ground movements. And I'll talk about using the case studies that we've done in Chicago over the years, illustrate some of the issues related with that, and then talk about some other sources of movements that occur besides the stress relief, those caused by stress relief from taking soil out of the ground. And that in itself could be easily another lecture. I just want to mention, we'll give one example of that, something related to top-down construction and how the effects of the time-dependent response of concrete can have an impact on lateral movements, and then make some concluding remarks. So this has been known for a long time, that if we look at the earth pressure diagrams for sands, theoretical earth pressure diagrams, say the Rankine diagram, provided a distribution of lateral pressures where the soil pressure increased with depth. And experience had shown that that really didn't work when you were looking at designing supports for excavations in sand. The issue was that the pressures were higher at the top of the cut and lower at the bottom of the cut for excavations in sand. And this was noted by Terzaghi as early as 1936. Okay, and I think this is a common problem we have in geotechnical and engineering, and in fact, it's probably extends to many other things in life, where the great philosopher Yogi Berra said, in theory, there's no difference between theory and practice, but in practice there is. And so he must have been a geotechnical engineer at heart, I think. So Professor Peck came up with the apparent earth pressure diagrams for Terzaghi and Peck. And basically, the way he solved this is not theoretically, but looking at field performance data. They measured loads in cross-lot braces from a number of sites. He looked at different soil conditions, sands. He decided to break it up into sands, stiff clays, and soft clays. And then at excavation, he would look at the loads in the brace, divide by the tributary area to come up with some pressures, select the maximum apparent envelope pressure at each level, and then for all the excavations in a given soil type, he defined the envelope of maxima. So this is clearly a loading diagram and not a pressure distribution. But this became the standard of practice for many years. And all the details of this that you can find in a PhD in 1966 by Flott at the University of Illinois. Very, very excellent document. If you have the time, take a look at that. So here's just one of the diagrams for soft clays. You can see the database was extensive, 9 from Chicago, and those all pretty much came from the station, some of the cut and cover tunneling and the stations at Chicago in Professor Peck's experience as an assistant subway engineer. 9 from Oslo, a couple from Japan, and 1 from England. And so a very simple diagram, a trapezoidal diagram. The ordinate of the pressure is equal to the hydrostatic pressure ratio, not the active earth pressure coefficient, but the hydrostatic pressure ratio as they defined it. And that was equal as a function of the undrained strength of the material above the bottom of the cut, the average undrained strength of the material above the bottom of the cut. And so this became the standard for designing excavations. And one of the things is that when you look at these, the reason you had to go to this is that there was quite a bit of variability. And there's many factors that affect strut loads, aside from the obvious whatever the earth and water pressures were at the time. Workmanship, some of the details can be, well, maybe they don't quite brace very well and you don't get the whales up against the struts or against the wall. We can look at preloading. You can preload, cannot preload. You can preload like this by using 2 spreaders and spread apart whales, or you could put a jack on an individual cross lot. And the amount of preload that comes in there has an impact on the loads that you're going to remain in the strut. And also, in many environments, temperature is very important, particularly if you put your cross lot in the cold weather and it's in service all the way to the warm weather. Steel tends to expand, it pushes against the reaction against the wall, and you get some very high pressures there. So all these things make it very difficult to theoretically predict any kind of earth pressures on the support elements. Those diagrams have worked well, and they're still in practice for flexible excavations today in many places. He also mentioned in 1969 that you could quantify the settlements in this diagram, where on the vertical axis is the settlement divided by the depth of excavation. So that is a normalized settlement, and it's plotted at a normalized distance from the excavation wall, and that's the top diagram, the distance from the excavation over the depth of excavation. And he found out that there were 3 zones, and those zones, that's 1% of movement. So the settlement divided times 0.01 or 0.1% is equal to the maximum movement. And most of the data fell in zone 1, but as you got softer clays, you fell into zone 2 or zone 3 with very soft clays to a large depth below the cut. And when those diagrams were first developed, the very soft clays in zone 3 were really Mexico City. And you could also get in there if you had other problems besides just excavation relief. And in particular in Chicago, if you had problems with caisson installation where you had a significant amount of soil squeeze while you put in drilled shafts, which part of the foundation for the building that you were making, or if you had water problems and you had a pump from the bottom of the casing, you'd take out fines, and then you could get yourself into zone 3 but even within very good soil conditions. So construction had a big impact, always has a big impact on what goes on when you're making an excavation in terms of the numbers. So one thing that you do when you have this very conservative loading diagram, you wind up with a very redundant or conservative system. And so what you can see here is this looks like a forest of cross lots in an excavation in Chicago. And what you see is a localized failure. The whale is kind of buckled up there, and it was not really a problem. The load was because the system was so redundant, the load was transferred to the adjacent whales and the crosslots, put a little T section at the top, and it was fine. And the excavation, in terms of stability, was fine. So picture that back in the, the pre-1980s, this was pretty common. So if we summarize stability-based design, first of all, it arose from the field measurements of the loads and the bracings. And that was what Professor Peck's main contribution was this. It is a conservative design based on apparent earth pressure envelopes, and it generally leads to a very redundant system. And at the time, there was no real serious consideration about the movements that occurred when you made an excavation. Now that all changed as the 1980s developed, in 1970s, when deeper excavations were made in urban areas and you started impacting adjacent buildings and causing damage. And so it became apparent that there had to be some sort of design for ground movements. And so if I call it a serviceability-based design, that you want to select the support components to maintain ground movements to acceptable levels. Now those acceptable levels, we could easily spend an hour talking about what is an acceptable level for a given excavation in a given situation. We will assume for this talk that we know what that is and we're going to design to that level. The serviceability-based design really became possible when people started applying finite elements to excavation support problems, and particularly the work by Clough and his co-workers in the 80s resulted in a semi-empirical approach based on system stiffness and factors of safety against basal heave. Now their approach was for clay excavations only. And today I think it's a true statement that you are not only using finite elements to estimate movements, but you're using it I've seen it used many a time to compute the support loads in the bracing, okay? So in the 80s then, there was much effort for this, and Clough and O'Rourke in 1990 presented an excellent paper in the Lateral Earth Pressure Conference of that year. And keeping the same zones of settlement as Peck did, they looked at the plot, the settlement versus the excavation depth. And so it's the same plot, I think a much better plot because you see where the data falls in here. And so they looked at in this case, about 15 case studies, plotted the data up, and that's a lot of movement, quite a bit of variation. So one question you might ask, why is all the emphasis on soft clays? Well, if you look at, they did the same thing for the sands and the stiff clays, and if you look at the magnitudes of the movements there, the envelope of the settlements, maximum typically is 0.3% for sands and hard clays, and more likely 0.15 to 0.2% for the movement. So clearly, you get much bigger movements in soft clays, and so that's why there's so much emphasis in this area, okay? So since I'm going to talk about excavations in Chicago, I only want to really talk about the stratigraphy once, so we don't have to look at it. There's obviously minor variations, but classically you've got an urban fill at the ground surface, overlying a sequence of increasingly stiff glacier deposits. Sometimes, not all the time, but sometimes there's a desiccated clay crust at the surface, followed by sequences of increasingly strong and stiff clays. One thing you notice, the Blodgett stratum is the softest of the clays, other than some infills from old channels, has very high variability in water content. And this comes from the fact that this typically is thought to be anyway a superglacial till. Below that, there's a Deerfield stratum, which is a medium stiff clay that is noted by very uniform water contents. Below that is the last of what Peck called in 1954 the lake border clays, Park Ridge stratum, which is also a glacial deposit, over basal tills, which is locally in Chicago is known as hardpan, and that can be extremely strong. So that's the basic idea. Most of the excavations of typical depth bottom out in the Deerfield stratum. So you've got some relatively soft clays below the stratum, and depending on where you're at, that could be significant for relatively significant depths or not. So to make movement predictions then, it really depends on the soil conditions, the retention system stiffness, and of course the construction procedure. That can have an overriding effect on anything that we do. And so I think it's always wise to make this a two-step process. One, look at precedent, look at those, and many people have done work on making compilations of movements in excavations since O'Rourke and Clough, but there are essential findings that keeps being substantiated. So you can look at precedent to get some idea, but you really need to look at some site-specific conditions for a number of reasons, and typically that's done generally with a numerical method. So if you're going to do a numerical method, you have to have, the goal is to make whatever goes on out in the field go on in your computer. So you have to be able to accurately simulate construction and have proper finite element procedures, and your constituent model has to be good enough to represent the response that you're trying to represent in the field. So we'll have a little bit more about that later. And of course, when you're doing this, you need to have instrumentation field verification. So this is where the field performance and the case histories become extremely important. So I'll first start with the Chicago State. I will talk about several excavations, but one is the excavation that took place at the Chicago State, and this was for the renovation of the Chicago State subway station, which is one that was one of the cases that turned up in the Terzaghi and Peck loading diagram. Now, the excavation you see in front of that school, that's a 3-story building as a St. Francis Xavier Ward school. That part of the excavation was a tunnel. So that was designed, it was constructed with tunnels, with a tunneling operation. So the goal here was to, you can see this turned out to be about a 40-foot cut, and the 3-story school is founded on shallow foundations. The Holy Name Cathedral, which is behind it, the larger building behind it, was on drilled shafts and wasn't really an issue. So here's the picture of the support system, and you can see that it's a cross-slot brace at the top with 2 levels of ground anchors, and with the existing tunnel that was going to be renovated below that. And you can see that you had the Ward School had a one-story basement, so that was about a 14-foot deep cut. And so therefore, if it's a 3-story building, you're getting a net stress relief on that side compared to the stresses in the ground from the other side of the excavation, which basically was a parking lot. So there was higher stresses on the left side than on the right side of the figure as you look at it. And you can see the typical soil conditions. So this support system, the goal was to come up with, this was a value engineering last-minute change because the original design was rejected. And so there was no time for any really detailed analysis. This was around the 1990s because of the time constraint. So basically the design was essentially done with the Clough empirical charts and an analysis by a structural engineer of how those perceived deformations would impact the adjacent school. And we came up with an allowable settlement of 1 1/4 inches. So at this time, that was kind of beyond what we were getting in Chicago, and so there was a very detailed monitoring program here. And so what you see in red are locations of inclinometers, and 3 on the side between the C-compile wall and the building, the school. And the W's and the C's are locations of settlement points on the walls and on the columns in the basement of the structure. So those were monitored weekly throughout the construction process. And the inclinometers were read several times a week. Okay, so this figure is a detailed figure, but it shows everything, and I include this in there because I think it's very important to make sure you have a very detailed record of construction that you won't find in the daily field reports. You have to be able to look at what the excavation level was at the particular instrument that you're looking at, as well as what is going on in terms of installing a brace. So the ones up there that you can see represent when the C-compile wall is installed, and then the solid line is the excavation level throughout the process. And then, so the sequence was install, excavate below the first level brace, put the first level brace in by 2 and 3, excavate below the first tieback level, as noted by 4, excavate, so install the last tieback level 5, and then when you're finally done, you reach bottom grade. And then it was open for a long period of time without making a good connection. And so there was maybe some minor movements. And what you're seeing is a movement summary on the bottom, which is lateral movement or vertical movement, but lateral movement for the colored dots. Those colored dots represent the lateral movements of the inclinometer between the wall and the school at different elevations. Elevation 3.7, or the top blue one, was in the soft clay and represented the maximum movement throughout the process. And then the other two are at lower depths, where the last one at 11 was basically at the bottom of the cut. And then there was also the school settlement marked by W10, which is on the lower part of the wall, that was exactly right adjacent to the inclinometer, and you could see that that kind of tracked the lateral movement in the soft clays. And what you can see is that after the installation of the C-compile wall, remember the target movement was about 1¼ inches, which is about 35 millimeters. Well, it already had 10 millimeters of movement. And so this was kind of may create some consternation because nobody really thought putting in the C-compile wall was going to create any ground movements. So that was a third, you're taking a third of your allowed movements right from the start. And then nothing really happened until you excavated below the crust, and that occurred, you could see the acceleration of the movements until the end of the excavation, where the maximum movement was a little less than 30. So that looked pretty good. Although at that point, you got some continued deformation until the base slab was poured and the whole excavation was firmed up. So you can see that about the bulk of the movements occurred during excavation and support. That's what we predict when we look at finite elements, but we had a 10 millimeters due to installing the C-compile wall, and then some time-dependent movements at the end of the project. So how did this look in terms of more conventional inclinometer and settlement data? Well, this is one of the inclinometers between the school and the C-compile wall on the east side, and you can see that the first data set represents the entire lateral movement during installing the C-compiles, and you can see that the movement was about 10 millimeters, again, focused in the soft clay. As the clay got stiffer, there were still movements, but they were smaller. And that deformation pattern was reflected in the settlement of the columns in the Ward School, okay? And then if we looked at the excavation, we got the same sort of thing. Another 20 millimeters of movement maximum, and reflected in 20 millimeters settlement. So these aren't all the inclinometer data, but this is enough to show the general trend. So if we just summarize this stiffness-based support, the design and support system, first of all, necessitated detailed performance monitoring. There was provisions in there that if you had to add another tieback level, you could. But the movement levels, initially, was very concerning, but then it became, by basically nothing more than compensating errors, because we forgot to add in the C-compile movement, we under-predicted the movements due to the excavation, and so it worked out fine. Like many things, you'd rather be lucky than good. So the requirement then, though, because we were looking at such small movements, allowable movement of 1¼ inch was pretty unprecedented in Chicago at the time, and you really have to think about all the different sources of movement. And so the C-compile wall installation and the long-term movements were something that eventually have to be considered. But what I brought this case up for to start with is that because we had this detailed data, it allowed us to develop what I might call an adaptive management approach to this. So basically what this does is you quantitatively evaluate the performance of a system based on field observations. And if you make these observations early enough, you can use these observations to update your performance predictions, and you plan the project so that alternate procedures can be applied depending on the observed performance. So this is definitely a design approach. You think about these things in the beginning, you make your predictions, you get your target levels, and you provide alternatives at that time. The Chicago State project, for instance, it was clear that we were never going to prevent any kind of damage in that building. The target was some minor architectural damage, which I'd like to present, but not enough time. So the fact was, though, that by doing that, at the beginning, the contractor was allowed to put in a bid item in his package to allow to pay for any damage to the structure. And between that cost plus the cost of the C-compile wall was much cheaper, saved a lot of money compared to, say, a structural slurry wall that was a possibility. And, well, it was still much cheaper. And I don't know if you would have gotten less movements with the structural slurry wall in any case. So it's really a design approach when I'm talking about this. So it's here's the flow chart. You come up with an initial design on the left. And the initial design, if we're thinking about movement predictions, we're talking about making some typically numerical procedure, finite element, finite difference, take your pick. We've always used finite elements. That becomes, you know, the initial design is the input to the prediction. You make your calculation and come out with your numbers. In this case, we'll look at lateral movements behind a wall, close to a wall. So on the right side, we're monitoring, and the monitoring has to, of course, consider the observations that you're making, as well as a detailed construction record, because otherwise you can't really do this very well. So then what we do is compare those two. We minimize the difference between the computed and observed responses using optimization routine, develop new parameters, and with those new parameters you can predict the performance as you go on. Okay? So just one thing, I just want to show exactly what I mean by this. You start out with a finite element run, and you compute an objective function, and that objective function is nothing more, y is the observed movement, a lateral movement at depth, and y prime is the computed value, and y prime sub b is the computed value as a result of a change in b, which is one of the performance prediction parameters. So that's just the sum of the squares for the objective function that we're using. W is a weighting function. So to do that, we use a gradient method for optimization, where you compute the sensitivity. And for this, you need to look at, for each particular parameter. So it might be a stiffness parameter in 3 or 4 layers. You perturb that by a small amount. That's the only thing you change in your simulation. You get your change in the response that you're trying to get, which in this case, say lateral movement with depth. And you do that to come up with the sensitivity matrix, which is those terms that come in for the x, the rate of change of the value with respect to the change in the property. So we do that, say 5 times if we have 5 different parameters, and then you can once you get that, you perform your nonlinear regression with that sensitivity matrix. That can be done with MATLAB. It's a standard off-the-shelf procedure now. And then you check if the model's optimized. If it is, then you come up with your new parameters and you make a new finite element run. This whole sequence can be linked together with macro programming languages, and it takes 4 to 5 hours on a PC to do for 2D. So it's something that's very reasonable to get. So the key elements of the approach are, first of all, the prediction method, the finite element method. But keep in mind that you can't always get all aspects of the construction process modeled correctly. You have to have the observations reliable, accurate, in timely fashion. So this was, when we started this business, this was the hardest part, was getting the data back. If you had some outside agency take inclinometer readings or survey readings, you wouldn't see it for 2 weeks, and by then, you know, you were gone, and there's nothing you could do about it. On the other hand, nowadays, things have picked up considerably about that, and we'll talk a little bit about that later. The constitutive model has to have the capability to replicate the behavior that you're trying to observe, and what really is good about this, it allows, remember, when you start out in design, you have to predict the construction procedure. That's as hard as anything else as far as I'm concerned in our experience. But the value of this is that when you come to making the analysis at a given stage, you know that you take the records, you know the construction procedure. So that becomes a known and not known. And the other thing is that the contingency, to make this work at all, you have to think about this in design and have your contingency options prepared at in the design phase of the project. So I just want to then show very quickly how we can use, how this was used, and this again is that Chicago State project, where we optimize the parameters at an early stage of excavation to come up with the predictions later on. And so this we used the computer code Plaxis. It was Plaxis 2D. I forget what version because it was a while ago. We used MATLAB, the optimization routine, and we used the hardening soil model, which is a nonlinear elastoplastic model. And we used a stiffness parameter called E50 reference. And that E50 reference is kind of a plasticity parameter. It's not an elastic parameter, but it's basically the tangent stiffness at 50% stress level. And the reference refers to the fact that you can relate that to the vertical effective stress. So one parameter can go for a soil deposit where the stiffness increases with depth. So, but that's a stiffness parameter, and you do that for several soil layers. And so the model that we had is seen here, and what you can see is that these red lines represent the 2 inclinometers, one on each side of the excavation, that were used as the basis of the prediction. So those were our observations. We had data on both sides of the excavation. The simulation included simulating the tunnel to get the right stresses in the ground, simulate the construction of the school, simulate the excavation of the installation of the walls, and then the normal excavation sequence. So here's the first set, and we started with soil parameters that came from tube samples, in fixed piston samples, even in the soft clay, without any corrections, because we knew there would be some disturbance. So typically you're going to get a softer response predicted directly from the laboratory results, no matter how careful you are. So what you can see on the top row is at the 5 stages. So stage 1 is the installing the secant pile wall. Stage 2, 3, and 4 are when the excavation was below each level of support, and stage 5 was at the bottom of the excavation. And you can see on the east, those were all 5. On the west, on the east, the inclinometer was protected between the school and the wall, no construction equipment. And for anybody that's worked in these situations, you know that if you're not really careful and you leave instruments exposed, they tend to be destroyed. And so we made the inclinometer on the west side of the wall, made it through 3 stages of excavation. So we at least have that data. And what you can see is that the solid lines, the solid dots represent the observations from the inclinometers, and the observed are the open symbols. And clearly we got larger deformations predicted using the exact construction procedure. And this is after the fact. So again, soil parameters are based on laboratory tests, and we wanted to know this when we were starting out because we knew the correction should be the other way. We wanted to make them, we would think that if we start with a softer parameter, the parameter should get stiffer so we know kind of what's going on. So what we did then was use that first stage as the optimization. So that's when the secant pile wall was put in, and you optimize that data set. So inclinometer on one side of the wall, inclinometer on the other side of the wall. We got best fit parameters based on that. We ran through our analysis for that. And of course, for the first one, it's a good fit because, of course, you're making it match, all right? But then for the rest is not a prediction, but it's a computation based on the results of the first analysis, stage 1. And you can see the improvement is significant. And in fact, we're able to pick up, say, if you look at stage 3, by that time, you even have more movements on the west side due to the larger loads there than on the east side. And that was picked up with the simulation and the parameters that were developed. So I think we were pretty successful in that. Okay, so that was good. So now we have a method that you're able to come up with a set of parameters based on field observations, not just laboratory data. So then the next step would be, well, what about using those as starting parameters for other excavations in similar areas? So another excavation we worked on was for the Lurie Center in downtown Chicago. And we made this simulation. This was a significantly different support system. This is a sheet pile wall supported by 3 levels of ground anchors. And we looked at a plane strain analysis here. And so what we wanted to do was, again, using this. The ground conditions were a little bit different here because this is closer to the lake. So you have a beach sand deposit that goes down about 5 meters. But then you got the soft to medium clays and stiff clays and hard pan again. And you can see this is just a computation with the actual construction procedure, again, with the Chicago State parameters and looking at the results from the computed value. So the field data is the open circles. Plaxis was the platform we used for the computations. And you can see in the beginning of this, we see that we're over-predicting the movements, okay? But as we got more and more deformations, we got a much better prediction. And so by the end of excavation, that's pretty good estimation of the ground movements, all right? But in the beginning, we weren't. And this is one of the limitations of the model we'll talk about in a minute. So that was one project that, well, again, using the Chicago State parameters, we adjust a little bit for the differences in stratigraphy. We get a very good fit. We did the same thing for a Ford Center excavation in Evanston. And this is, again, a different excavation support. Again, sheet piles, but now with 2 levels of cross-lot braces. You know, there was a building that was fairly close, supported on shadow foundations, and so the movements were a concern here as well. And so this was going to be simulated again. We took a cut all the way through the building just to get the difference in stresses on both sides of the excavation. And once again, when you look at the computed values with Plaxis and Chicago State, they are bigger than the field values. And again, but these movements are small. So these are about half the movement that we were getting at Chicago State. So clearly the model we used in this case could not take into account that entire strain range. And so what we did is the Deerfield stratum, again, that's the stratum with the uniform water content where you're where your cut is made, is bottoms out. This is the optimized parameters in KPA for E50 reference for these 3 projects. And what you can see is we can use the finite element to calculate average shear strains in the soil mass adjacent to the wall. And you can see the higher the shear strain, the lower the optimized parameter. And that's because the nature of this model does not include small strain stiffness. And so if you're going to make these predictions at early stages, you need to have that small strain stiffness built into your model, or you're going to keep changing the parameters, which as an exercise is okay, but not really predictive. So as part of this work, we always would go out and cut block samples from the excavations, bring it back into the lab, and do a little more detailed testing, including bender elements at the top to get the shear wave velocity for, based on wave propagation, and then internal instrumentation to get better measures of shear strain or strains in the soil, give more accurate measures of that. So we did this on a number of excavations. It's good to be the professor here, standing here, and not being the poor students down here. But I will cop to the fact this was our 3rd time we did this, and my back hurt, so I couldn't get down there anymore. That was my excuse, and I was sticking to it. So this is a typical result from one of the excavations we made. This is called Block 37. And so what we're doing, a plot here on the left is shear stress versus, this is an effective stress plot, so somehow the Q. That should be shear stress versus mean normal stress. So these samples were K0 consolidated. Again, these are the block sample results. These materials were lightly over-consolidated. So we brought it back to the vertical effective stress, and then we sheared it. And so what we plotted is the shear stress versus shear strain relationship that we found from our data based on normalized shear modules. So this is a typical plot you might see in earthquake engineering typically, where you plot the ratio of the secant shear modulus versus the small strain shear modules. And so the limitation of the models is this, is at best, if you're measuring your data in a conventional triaxial cell, where you're measuring movements outside the cell by looking at the rod going up and down, you're not going to be able to measure at best 0.1% strain. Okay? So if that's 0.1% strain, and your average strain is maybe down at about 10%, so maybe something, your average strain is over here somewhere, then you can see that you're going to miss quite a bit of stiffness there. And all that increased stiffness is going to make a difference in any kind of movement prediction you're going to make. And the problem gets worse if you have a simple model. Now, this model is the hardening soil model that was not completely nonlinear from the start of deformation. Now, if you took any kind of elastic, perfectly plastic model where you represent the behavior as one shear stiffness, G, how do you pick a shear modulus depending on the direction of loading or the strain level and expect to make any sense out of a movement prediction? You can't. So at most you get is an approximate. Simple models are good for looking at stability problems, potential basal heat problems, but in terms of deformations, you can't use it. Okay. And so to really show this is that you can look at some simulations with the same basic model parameters for model as much as you could be anyway, between Moore-Coulomb, hardening soil, and hardening soil small, which is just, he has a small strain overlay on top of the conventional hardening soil model. And what you see is that the Moore-Coulomb always under-predicts the maximum settlement and gives you smaller distortions, but over-predicts the extent of movement. So the settlement trough goes out further if you want. Whereas as you get more complicated and you get down to the hardening soil small with the small strain stiffness, you get more settlement and in a shorter area. That means you get more distortion. And of course, distortion, if you got a building behind it, the more distortion you got, the more damage you're going to get. So you want to be able to look at that. Okay, so enough about that. So I just want to use this project that was recently completed, the SQBRC excavation, another one in Chicago. It was it was a sheet pile wall supported by 2 or 3 levels of tiebacks. You can see the ground anchor line, the tiebacks here, large cross braces. There's the 3rd level of tie. In some locations, there was a little bit more excavation locally, and the 4th level of tie was put in. But again, sheet pile wall with several types of excavations. Here's just a cross section. Again, this was by closer to the lake, so you had the beach sand, the medium clays and stiff clays were done. Were the soils that were being optimized, the data. But by this time, though, this was a recent project, and things have gotten much better. We use shape acceleration arrays. First of all, this project was done, our partners in this project was Hayward Baker and their company G-Tech. G-Tech developed a great project website where you were able to take the shape acceleration arrays, so these are your in-place inclinometers. The data would get to the website basically in real time. There was a robotic total station to get settlements in real time. It went to the website. There was a web camera, so if you weren't at the site, you could at least keep track of what was going on. I mean, you still need to go out and measure things, but it helped a lot. In the project website. And so what we're able to do with this is then we can take the data in real time, say, 10 minutes after it gets posted, pull it off, do our optimization process, and put it back in and have an updated prediction in about 4 hours, which I think is pretty good. And so the project website had the design predictions and then our updated predictions as we went. And that wasn't, it was for the people, of course, the shareholders in this particular project could look at that. So anyway, again, here's the typical deformations, lateral wall movements versus the maximum lateral wall movements. In this case, the values were taken at the elevation where the maximum value occurred. These are 2 shape arrays on the north wall. This, again, is the excavation sequence in front of those 2. And what we'll do is look at what happens at stage 3, 5, and 7. So in this particular case, you can see the movements are, again, about 40, 45 millimeters, 1.25 inches, 1.5 inches. And they accelerate greatly when you started excavating into the soft clay. So again, when you stress the soft clay, that's where you get your movements, not too surprising. So this is just the wall movements as the excavation is below the strut. So the strut, in this case, is marked by this black line. So that's the cross lot that you saw. And so as you excavated below that, that was stage 3. So by stage 3, that's this data here, you can see that, oops, let's go back one. You can see that you had maybe about 2/10 or 4/10 of an inch of movement in the soft clay, and in the stiff clay, you were less than 1/10 of an inch. So it's more than likely, in fact, you couldn't, that was not enough movement to be able to optimize with any degree of accuracy. So what we did was look at what happened between stage 3 and 5, and that's when you first got into the soft clay. Good design. They put the anchor is, well, good design for number 1 because the anchor is put in to avoid problems putting an anchor through a saturated sand, through a sheet pile wall. But 2, you're getting the excavated level as soon as you can, get the support in as soon as you can before you get into the soft clay. So that minimized the step. But you still see 3/4 of an inch of incremental movement during that time. So we had large incremental movements there. All right, and then as we got to stage 5, we went down below the next level, and you had a little less movements, but still continued movements as you went on. So again, to be able to evaluate this, we wanted to look at this using, again, we used Plaxis, MATLAB, and we used the hardening soil small model here. And these are, on the left-hand side, use optimization using stages 3 and 5. We have to use 2 parameters. If you're going to use small strain stiffness, you have to have some parameter for that to optimize, and then the same E50 reference. Gamma 0.7 represents the point where the shear modules has been reduced 30% of what it was based on wave propagation measures. Okay? They have cross-lot data, or cross-hole seismic data, and CPT data, so we know the actual G0 pretty well at these sites, but we didn't know the degradation. So that was the parameter we optimized. And on the left, you can see the optimized values are in color. The open symbols are the measured values. And of course, if you're able to optimize, you're able to get good agreement, and that shouldn't be surprising. But on the other hand, when you look at stage 7, which is really a prediction, and this was a prediction that we put up into the website, that you saw that the prediction was very good. I mean, I don't think you can get much better than that. So we were very happy but you need to get some movements to start it. Now you can see what happens with the hardening soil model. Again, we tried to optimize just the E50, and the fit at the stages we were trying to use to get the parameters was not as good. I mean, those lines are not falling on top of one another, right? Whereas, and then when you went to the prediction, you wound up not predicting very small additional deformation as you went to 7, to below the next tieback level, and we basically got a very poor prediction there. So again, an emphasis of needing a model that takes this into account, and to get the best benefit out of this, you really need to look at the small strain stiffness. So how do we look at to summarize this? So the curtain capabilities, plane strain simulations, Ideally, you would like to go to 3D because you have to wait until you get more or less plane strain conditions at an instrumentation location to apply your model. So 3D would be good. There's a number of issues yet with that, I think. I think the soil model should include small strain stiffness, and the updates are possible in near real time, 3 or 4 hours after the data set if you have the right instrumentation out there and the data acquisition system. You can remove uncertainties with the construction procedures because you apply the process when you get down to a particular level. And it's a design approach if contingencies are included. And hopefully that's what's done. There's no reason to do this without that. And then you cannot simulate all activities. And so I'm almost at the end here, and I just want to emphasize that there's movements from causes other than excavation, and I'm not the first one saying this, but many times when it comes to design, people forget about adding these things in there. So when you make site preparation, you could be removing foundations. You wind up taking big hunks of concrete out. You break them up. That induces vibration. You're removing stress. You're moving soil from the ground. That can induce deformation. Wall installation. We talked about secant pile wall, but slurry pile wall is the same way. Sheet pile walls, you get permanent deformations in sheet pile wall. You're displacing soil. I mean, it's a solid element going into the ground, and it's going to force the soil off to the side. You can get densification during driving if you have loose sands at the surface. Those will densify locally when you vibrate a sheet pile in. And you can install deep foundations can cause ground movements that can be significant. But ones that haven't caught a lot of movement is shrinkage, concrete shrinkage during top-down construction. Now, top-down construction really is a construction expediency, right? So the idea is you put your walls in, you put your deep foundations in, you cast your upper slab, and then what you do is go up with your foundation, with your building, and you go down at the same time. And what that does is stretch out the excavation time. So the excavation is not on the critical path, so it takes a lot longer, okay? So one thing you might think about is, well, when you cast your slab, those slabs are typically integrally hooked into a wall, so you get almost a full moment connection, and you're putting them in, and what happens? There's material dependence of concrete. One of those components is shrinkage, and so that's going to pull, do some strains, and pull the walls together. So I just want to illustrate this quickly with the One Museum Park West project, which was a 53-story structure, 45 feet deep basement. There was a central core with shear walls, and that part of the building was constructed with bottom-up methods, and conventionally reinforced slabs for the support, and those were used for permanent and temporary support for the wall system during top-down construction. And there were secant pile walls installed, as well as columns by straight and belled caissons. Straight shafts went to rock, belled went into the hard pan. So one unique part about this is we put in a number of strain meter stations where we put in vibrating wire strain meters at the top and bottom of the floor slabs on 4 levels here. And so the purpose of this was to kind of quantify the components of the axial loads in the floor slab and try to relate the strains that we develop to the shrinkage, to how much movement would be caused in the system by shrinkage. And so here's just one typical strain meter response. And so there's various causes of strains in a strain gauge, right, strain meter. So one is temperature effects, and first there's 2 components to that. That's one TC, that's temperature correction, and that's because the coefficient of thermal expansion of steel and concrete are different. That's going to induce a strain as the concrete strains. So that's a component. And then SC stands for the fact that if you change the temperature, the floor slab can go, or the support element can expand or contract. And so that's a structural compliance term, and we can quantify that as well. And you can see in this case for top down, because the top is covered after the first floor slab, you're kind of in the temperature variation is much less, because that's more or less heated. It was about, in this case, around 50 degrees pretty much the whole time. So there's not a whole lot of temperature variation, so those were relatively minor. And then what you see below that is the strains that were measured, and the blue is the top gauge, and the red is the bottom gauge. TD is time dependent and lateral earth pressure. So we get time dependent strains in the concrete, plus whatever happens from the lateral earth pressures and water pressures. And they separate. Where they separate there is you can tell right about that point. This is on on arithmetic scale. But right there is when they excavate below the bottom of the slab. It's a cast on grade, there's no difference, it's just axial load due to the shrinkage. And then all of a sudden you remove the soil beneath it, as you do in top-down construction, the material starts to bend, and that's where the gauges separate. And so what you can see is that about at the end of construction right there, that's when the slab openings that are always left in the holes, when those are finally closed up. So you're pretty much done with the earth retention system at that point. And you can see you had maybe 350 average micro strains, and then some significant strains that went on for another couple hundred days. And what were those is we felt that you know, again, you're building the structure on top of this. You got a central core, you got load-bearing walls. They're taking load. The Poisson effect is compressing the slabs a little bit, and I think that's what those additional loads were. So again, we were able to get to the point where we kind of knew what that was, but the total strains we could isolate. But how do you separate out those two? And so there wasn't really easy to do. In fact, there was no way we could do that. So we did a numerical model using SAP 2000 to compute strains arising from the material time dependence. This was done, a very detailed model. This just shows the support that went in. So you got the wall, a cutaway here. So that's the wall, the secant pile walls. That's the central core. These are the foundations. There's the mat for the central core. And so the way this was done was sequentially. So we put the day 90 was just the secant pile wall was put in. The drilled shafts were put in next. The central core mat, and then the core was done. And then we get to this point here where we put the first floor slab in. And so that's when we activated the material time dependence, and that's indicated by the shrinkage strain rate. We used the input was the red symbols down here, which was the average of a number of published data on that. But you can see that shrinkage can be up to 600 days. So we activated the shrinkage in the floor slabs as soon as they were built. And so when the next floor slab in, we activated again, and so on until we were done with the excavation. There was no soil on the outside of this because we were just pulling the soil in, and we had beams on the inside representing the soil resistance due to the passive resistance. And so what we were able to do was to compute, with the model, the open symbols there, which is the material time rate dependence at various stages. So stage 9, 14, and 18, that's basically 18 is at the end of the excavation. And you can see that you get up to, again, oddly enough, about 10 millimeters of movement of the 30 observed that only observed during top-down construction. That's a significant part. So again, you want to be able to make sure that you take that into account. But on the other hand, if you're using the inverse procedure that we're having, one of the main assumptions is that the differences, because we take the construction is known at the time we make the analysis, the main assumption is that the differences in the observed and the computer response is strictly due to the soil response and the soil parameters we picked. But if you assume that, if you don't take this into account, you're assuming you're getting, say, 30 millimeters of maximum movement, of soil movement, when actually the contribution was maybe 20 millimeters of soil deformations of strains. So the strains were contributed by the concrete time dependence. So in this case, sum this up, 30% of the maximum lateral wall movements for this case, but it's important when the allowable movements are small. And all these things, more and more, you know, in Chicago, if you just have utilities, there's a 2-inch lateral, a 2-inch movement any place is the target. So something like 10 millimeters, you don't worry about it too much. But once you start getting down to 1 inch, and that's being more and more in locations, now you got to be really careful about what you're going to add into that movement prediction. And so this is why you have to identify all the sources of movement here. And so if you're going to use the adaptive management approach, these movements will need to be estimated so you can attribute the stress changes due to stress relief, just truly that. And so finally, some concluding remarks. So I think field observations still form the basis of design of excavation support, whether it be stability or serviceability. So I think the legacy of Professor Peck is still there. I think the process of predicting, monitoring, and updating, so adaptive management is nothing more than an automated observational approach when you get right down to it. I think that's a very useful design tool. The relatively small movements that arise from sources other than stress relief not normally considered in design, may become important when allowable movements are small. And finally, I think the trend to use finite element simulations to size the support components, walls, wales, as well as cross-lots, or tiebacks, but cross-lots in particular. The approach minimizes the amount of support, which is why people, I think, use it, and it computes deformation, so it's a 2-for-1. But the fact is that the loads aren't based on envelopes of maxima, which is what precedent has always showed a lot for flexible systems. The temperature and effects are generally neglected, and you're using an idealized construction process. And if I had more time, we could show a number of cases where just the process of over-excavation made a huge difference in the response of the support system, even if it was designed with a T&P apparent earth pressure diagram. So you come up with a less redundant design by using finite elements unless you make that judgment professionally as an engineer to add some more redundancy in there. So generally, just going flat out, you're going to get a less redundant design. Movement predictions generally only include those from the excavation process. And if you're going to use finite elements to do this, it's fine. It's a good way to do it. It's a very aggressive way, I think, but it's been successful many times. But it does certainly warrant additional monitoring. And again, detailed monitoring. And again, that is another fact that lends itself to saying that Professor Peck's legacy still lives on. So, one last thing, to quote John Wooden, I think it's what you learn after you know it all that counts. And if I could be as successful as John Wooden was in my business, I'd be very happy. So if it's good enough for him, it's certainly good enough for me. So thank you for your attention, and